ML is a general-purpose functional programming language developed by Robin Milner and others in the early 1970s at the University of Edinburgh, whose syntax is inspired by ISWIM. Historically, ML stands for metalanguage. It was conceived to develop proof tactics in the LCF theorem prover. It is known for its use of the Hindley Milner type inference algorithm, which can automatically infer the types of most expressions without requiring explicit type annotations. Additionally, the use of this algorithm ensures type safety. There is a formal proof that a well-typed ML program does not cause runtime type errors. Overview: ML is often referred to as an impure functional language, because it encapsulates side effects, unlike purely functional programming languages such as Haskell. Features of ML include a call-by-value evaluation strategy, first-class functions, automatic memory management through garbage collection, parametric polymorphism, static typing, type inference, algebraic data types, pattern matching, and exception handling. Unlike Haskell, ML uses eager evaluation, which means that all sub-expressions are always evaluated. However, lazy evaluation can be achieved through the use of closures. Thus one can create and use infinite streams as in Haskell, but their expression is indirect. Today there are several languages in the ML family. The two major dialects are Standard ML and CAML, but others exist, including FAAA, a language that Microsoft supports for their .NET platform. Ideas from ML have influenced numerous other languages, like Haskell, Cyclone, and more. ML's strengths are mostly applied in language design and manipulation, but it is a general-purpose language also used in bioinformatics, financial systems, and applications including a genealogical database, a peer-to-peer client-server program, etc. ML uses static scoping rules. Examples: the following examples use the syntax of Standard ML. The other most widely used ML dialect, CAML, differs in various insubstantial ways. Factorial: the factorial function expressed as pure ML. This describes the factorial as a recursive function, with a single terminating base case. It is similar to the descriptions of factorials found in mathematics textbooks. Much of ML code is similar to mathematics in facility and syntax. Part of the definition shown is optional, and describes the types of this function. The notation AT can be read as expression E has type T. For instance, the argument n is assigned type integer, and fac, the result of applying fac to the integer n, also has type integer. The function fac as a whole then has type function from integer to integer. Thanks to type inference, the type annotations can be omitted and will be derived by the compiler. Rewritten without the type annotations, the example looks like. The function also relies on pattern matching, an important part of ML programming. Note that parameters of a function are not necessarily in parentheses but separated by spaces. When the function's argument is 0, it will return the integer 1. For all other cases, the second line is tried. This is the recursion, and executes the function again until the base case is reached. This implementation of the factorial function is not guaranteed to terminate, since a negative argument causes an infinite descending chain of recursive calls. A more robust implementation would check for a non-negative argument before recursing, as follows. The problematic case demonstrates a use of ML's exception system. The function can be improved further by writing its inner loop in a tail recursive style, such that the call stack need not grow in proportion to the number of function calls. This is achieved by adding an extra, accumulator, parameter to the inner function. At last, we arrive at list reverse. The following function reverses the elements in a list. More precisely, it returns a new list whose elements are in reverse order compared to the given list. This implementation of reverse, while correct and clear, is inefficient, requiring quadratic time for execution. The function can be rewritten to execute in linear time in the following more efficient, though less easy to read, style. Notably, this function is an example of parametric polymorphism. That is, it can consume lists whose elements have any type, and return lists of the same type. See also, Dialects. CAM, a dialect of ML developed at INRIA. OCaml, a popular implementation of CAML with support for object-oriented programming. Standard ML, a formally specified dialect of ML, and its implementations. ISWIM, an extension of Standard ML with support for parallel programming using futures. Hamlet, an interpreter aiming to serve as an accurate reference implementation and a useful educational tool. ML5, a research variant of Standard ML designed for distributed computing. MLKIT, a compiler for Standard ML featuring region-based memory management alongside with optional garbage collection. MLTON, a powerful whole program optimizing compiler strictly conforming to the definition Moscow ML, an implementation originally based on CAMLite. PolyML, the implementation used in the Isabelle theorem prover. SMLNJ, an implementation with extensions for concurrent programming developed at Princeton University and Bell Laboratories. SML.NET, a Standard ML compiler targeting the CLR, descending from a former JVM implementation MLJ. LazyML, an experimental lazily evaluated ML dialect from the early 1980s that paved the way for compilation of call-by-need languages such as Haskell and clean-dependent ML, an extension of ML with dependent typing that led to the development of ATS, RPAL, an educational language related to ML, CakeML, a readable print loop version of ML with formally verified runtime and translation to assembler. Other languages and tools. Haskell, another popular functional language with lazy evaluation. F, a functional language for the CLR originating at Microsoft Research, so closely related to ML as to be considered a milliliter variant. ACL2, an automated theorem prover in Common Lisp. Cyclone, a safe C variant influenced by ML, Mithril, and milliliter-like language syntactically close to C with an implementation forked from SMLNJ. Books, The Definition of Standard ML, Robin Milner, Mads Toft, Robert Harper, MIT Press 1990. MIT Press 1997. ISBN 0-262-63181-4, Commentary on Standard ML, Robin Milner, Mads Toft, MIT Press 1997. ISBN 0-262-63137-7 ml for the Working Programmer, Lawrence Paulson, Cambridge University Press 1991, 1996, ISBN 0-521-57050-6, Robert Harper, Programming in Standard ML, Carnegie Mellon University, 2005. Elements of ML Programming, Jeffrey D. Ullman, Prentice Hall 1994, 1998. ISBN 0-13-790387-1, References, Gordon, Michael J. C. From LCF to HOL, A Short History. Retrieved October 11, 2007. Robin Milner. A Theory of Type Polymorphism in Programming. Journal of Computer and System Sciences, 17, 348-375, 1978. https, cakeml.org/. External links, Standard ML of New Jersey, another popular implementation, F, and milliliter implementation using the Microsoft.NET Framework, MLTON, a whole program optimizing Standard ML compiler, Mithril, SML with a POSIX face, SML, SuccessorML.